So this is chapter 13, which is about decision trees. We will be focusing on three ideas of the decision trees. First of all, we have to describe classification and regression trees. After that, we are going to apply classification trees to classify new records, followed by applying regression trees to predict new records. And finally, we are going to apply ensemble tree models to classify new records. So before we jump into the decision trees, let's first recall that we are discussing supervised data mining, where the target variable, we do have a target variable, right? And we talked about two types of target variables. The target variable can be categorical, and the target variable can be numerical. If the target variable is categorical, then we are talking about classification model. If the target variable is numerical, then we are talking about prediction data mining technique, right? And we had examples of these techniques. We used linear regression models. We discussed these two in chapters maybe 7 and 8. And these are one of the most important prediction models. Also, we discussed regression, logistic regression as an example of classification model. For the linear and logistic regression models, the predictor variables may include numerical or categorical variables or dummy variables. After that, we talked about another two techniques in the supervised data mining techniques. The first one is the other one is the naive Bayes, right? Naive Bayes. The K is a data-driven method that classifies a new case by identifying the K nearest neighbors of the new case based on the numerical predictor variables. And you are the one who decide what is the best number of K, or the technology helps you to tell you what is the best K. KNN is used for both as a classification and a prediction, but in our case here, in this class, we used it as a classifier only. For the naive Bayes method, it's a family of classification models based on Bayes' theorem, but there is a strong assumption about the independency between the categorical predictor variables, but it does well in many of the real-life applications. So in this chapter, we are going to talk about another supervised data mining technique, which is called decision trees. Decision trees. And this one is nice because we can do this one. We can apply it in both numerical and categorical predictor variables. Also, it's used for both as a classification and prediction problems. So that's why this is one of the, it's one of the best techniques used. It's simple. We'll be talking about the details about that one. Before we jump into the features of the decision trees, let's look at first to the introductory case that we have in this chapter. Hayden, she's working in this Sunville Bank, and he heard that a recent decline in the bank's home equity line of the credit businesses. Hayden does not believe that the decline is due to the competitiveness of the bank's interest rates. After all, customers choose to bank with Sunnyvale for the superior service. He believed that, not just for the low prices. Hayden's intuition suggests that Sunnyvale Bank has not been targeting the right customers to market its products. So Hayden compiles 500 past customers data. Also, he collects age, gender, and income from 20 new bank customers. So the data include the age, sex, income, and whether or not the customer responded to the HELOC offer. 1. if the customer responded and 0 if the customer did not respond. So these are kind of the predictors, and this is my target variable, right? This is my target variable. And Hayden would like to use the data to do 2 tasks. Number 1, he would like to develop a classification tree for predicting whether or not a bank customer will respond to this offer. Also, identify which of the 20 new customers are likely to respond to the offer. So these are the tasks that Hayden is willing to do. So what is the decision or the decision trees? The decision trees are popular supervised data mining technique. Its output displayed as one or more upside down trees, one or more than one trees. It's easy to interpret, and it represents a set of if-then rules. And we have 3 types of nodes. The root node, we will be talking about this, we will see it by the way. The root node, which is the top node of the tree, which is the first variable to which a split is applied. Then we have the interior node or nodes. It's more decision rules applied here. And the interior node typically are between the root node and the terminal nodes. So the terminal node is the classification or the predictions given, and we have no more splitting occurs after the terminal nodes. So this is an example, and it's from the introductory case. First of all, for most of the technology, the left branch from the root node represent the cases whose variable values are less than the split value, and the right branch represent the cases whose variable values are greater than or equal to the split value. So in this example, the root node refers to the age variable. So we have the age variable here. So the customers who are younger than 50 years old are placed in the left branch, and the customers who are at least 50 years old are placed in the right branch. And these branches lead to interior nodes with more decision rules apply, which is now we have interior nodes. So in this example, this is a simple example by the way, the income variable is in the interior node, and the split value for a variable can be different if it comes from a different branch. So here, for instance, the split value for income is $100,000 for those customers younger than 50 years old, whereas it's $50,000 for those customers who are at least 50 years old. And the bottom nodes for the decision trees are called the leaf or the terminal nodes, in this case where the classification or the prediction outcomes are given. So for instance, if you look at the rules now, if the age is less than 50, then we go next to the left, and the income is less than 100,000K, then this customer will never respond or will not respond. If the age is less than 50 and the income is greater than or equal to 100,000, then the customer is going to respond, and so on. If the age is greater than or equal to 50 years old, but the income is less than 50,000, then the customer is not going to respond, and so on. So the splitting process is repeated until each subset contains only cases with similar values for the target variable. And the pure subsets consist of leaf nodes that contain cases with the same value of the target variable. This is, we call it pure subset, when you have only the same value of the target variable. Normally, the target variables, if the target variable is of a classification, or if it's categorical, then normally we're going to cover the case where it's binary, so 0, 1. And there is no need to further split pure subsets, so it's just a pure, right? because it just, consists of leaf nodes that contains cases with the same value of the target variable, so there's no need to further split pure subsets. The process is recursive because every split depends on the previous splits. And sometimes it may not be possible to reach pure subsets, so identical observations with different values of the target variable. So this is going to happen. And we are going to have examples about this. So we have two types of trees. If you look at it's a classification and regression trees, and we usually refer to this as CART, C-A-R-T. So we have two types of trees. The first one, or models. The first one, when you have classification trees, and in this case, your target variable is categorical. The goal is to predict the class membership of the future cases. But if the target variable is numerical, then the model we are going to develop or to estimate is the regression tree, and this is to predict the value of the outcome variable of future cases. And the CART algorithm splits the cases into homogeneous subsets based on the value of the predictor variables. Decision trees produced by the CART algorithm are binary, 2 branches for each decision trees node. Also, it built using partition datasets as we used in other methods, which is training, validation, and test datasets. What happens first? CART will first grow the tree using the training dataset. This is the first thing we do. Then we select the optimal splits of all predictor variables and all possible split values until no further splits can be made. And this happens how? Achieved when leaf nodes only contain cases in the same class or same outcome, or leaf nodes are pure subsets. In this case, and this is the general tree that we're going to develop first, which is we call it the full-grown tree. The full tree or the full-grown tree or the maximal tree, which contains the maximum number of splits to identify pure subsets. But we have a problem with this. A full tree or the fully grown tree tends to overfit the data, and this results in a low predictive performance when you apply to new cases. So this tree bits the noise rather than the patterns. So what to do? We are going to optimize this tree. We're going to look at something else. So we're going to do something which is called pruning the full tree. We are going to make simpler trees. It's kind of you're eliminating some of the variables and focus on the most important variables. So we will be pruning the full tree to a simpler tree. What does the pruned tree or the simpler tree is going to do? It's going to generalize better to a new data. We are going to remove branches to improve the ability to predict more variable or to predict more accurately, and results in a set of candidate trees with different levels of complexity. We will have two types of measures, performance measures. The RSE is used for the prediction regression tree, and the misclassification rate, which is used for classification trees. So RSE is for a regression tree or the prediction tree, the predictive tree or regression tree, and the other one is for the classification tree. And we are looking for the minimum values for the misclassification rate and for the minimum RMSE. So we will be developing two trees. One of them is called the best pruned tree. The other one, we call it the minimum error tree. So we have two things here. Just be careful. We have the minimum error tree. What is the minimum error tree? Is the least complex. Least complex. This is important. Underline this one. Least complex tree. It should be the least complex with the less, like the number of the branches or nodes has to be less. It's the least complex with the smallest validation error. This is the minimum error tree. The other one is the best pruned tree, which is, again, it's the least complex tree, but with one standard deviation of the minimum error tree. So we have two trees here we are going to develop. Sometimes you will find that the minimum error tree is the same as the best pruned tree, so you will get the same tree. We will see this in an example. The best pruned tree can be used as your final model. And this is true because many in different softwares, they use the decision trees using different techniques. Also, not only this, even in R, by the way, in R we have many packages and libraries, they are using trees, in different ways. So R, one that we're gonna use is implementing the k-fold cross-validation technique. And we are going to do as we did before, we are going to partition our data into training and validation data sets. And the validation data sets will be used to select the optimal model complexity. Also, it's going to evaluate the performance of the model. Why the cart is popular? First of all, as we said at the beginning, it deals with both categorical and numeric target variables, and there is no need here to do any transformations most of the time for your data. It's easy to understand, easy to interpret, and easy to implement. It's one of the nicest methods that data analytics use. And the selection of the most discriminating predictor variable is automatic through the recursive partitioning and pruning, which is the one that appear at the top of the tree, which is the most important variable, the one that appears to be the top node, right? So the software does all of this. There is no need actually for us to go into the math behind this, the Gini impurity or other techniques. No assumption of the type of the relationship between the target and the predictor variables. There's no assumption here. You don't have to be worried about assumptions to be met like naive Bayes. We have like assumptions that, hey, the predictor variables, they have to be independent. But in this case, no. And it handles incomplete data. And the most important thing, by the way, it's not affected by the outliers. What are the drawbacks of this? You need a large training data. The word large here is subjective, by the way. Depends on the software that you're using. But normally we have that large data. We have that like in hundreds and thousands, in thousand, let's say. And it's expensive in terms of the computation cost, because if you have many predictor variables, it takes time to produce your trees. Also, if the number of the cases have been increased, then the time used to produce the trees is going to be really long. And the other problem with these trees is any small changes to the training data, it will result in drastically different trees. And we have a kind of solution for this when we talk about ensemble trees. In the next video, we will be talking about the first type of the trees, which is the classification trees.